Hi there, this is Astrophysics, this is Cosmology Lesson 3, and this is Hubble's Law and the Age of the Universe. Right, so in 1929, after plotting redshift calculated speeds of about 30 galaxies against their distances, Edwin Hubble noticed that there was a rough straight line through the origin that was obtained. Obviously there's a bit of discrepancy. Hubble's law can go anything between around 60 to 80 kilometers per second per megaparsec. Hubble said around 68. The data sheet one is under astrophysics and the options for astronomical data, and it's 65 kilometers per second per megaparsec. So Hubble's law states that the speed of recession of a galaxy is proportional to their distance. So V, recessional speed, is proportional to D. Constant of proportionality, H, and H is the Hubble's constant. So there you go, 65 kilometers per second per megaparsec. So a megaparsec is 3.26 million light years, because one parsec is 3.26 light years. When you're using the equation, the speed must be in kilometers per second, and the distance must be in megaparsecs, okay, to match up with the constant. Hubble's law does not work for some nearby galaxies. So Andromeda, for example, Andromeda's blue shifting, so it's moving towards us. So obviously Hubble's law doesn't work in a local cluster. Right, let's try an example question. So if you want to have a go at this one. So question 1, calculate or state the speeds expected for galaxies at distances of 1 megaparsec, 10 megaparsecs, and a billion light years. So first one, V equals hd, so velocity or speed is Hubble's constant times distance. So 65 kilometers per second times 1 megaparsec gives us a recessional speed of 65 kilometers per second. 10 megaparsecs is obviously 10 times that, because V is proportional to D. So if you've got 10 times more distance, you'll get 10 times more speed. And a billion light years, you have to do a billion divided by 3.26 million, so that gives us 306.7 megaparsecs. And then times that by the 65 kilometers per second per megaparsec. So that gives a speed of 19,900 kilometers per second. All right, let's try a second example. Slightly trickier, but should be fine. All right, so if you want to attempt this one. So question 2, calculate the distance in light years. So we're going to have to do a conversion there. To a galaxy if its recessional velocity is 10% the speed of light. So, first of all, we need to get the speed of light. So, 3 times 10 to the power of 8. Times 0.1. Which is 3 times 10 to the power of 7. Now, you've got to be careful here because that's in meters per second. So, we need to turn that into kilometers. So we need to divide that by 1,000 meters to get it into kilometers. So that gives us 30,000 kilometers per second, which we can now use for Hubble's law. Because remember, speed has to be in kilometers per second. Then we're just going to use Hubble's law, so V equals hd. So distance will be the speed which you calculated divided by Hubble's constant. So we've got 30,000 kilometers per second per megaparsec, kilometers per second divided by, and then it's 65 kilometers per second per megaparsec. So as you can see, the kilometers per second will cancel. We've got a divide per megaparsec, so that comes up to the top. So 30,000 divided by 65 gives us 461.5 megaparsecs. Then to finish, the question wanted it in light years, and a parsec is 3.26 light years. So we need to do 461.5 times 10 to the power of 6 parsecs times 3.26. And that gives us 1.5, get rid of that. 1.5 times 10 to the power of 9 light years, or 1.5 billion light years. Right, hopefully that one went okay. Right, let's move on to the expansion and estimating the age of the universe. Right, the expansion of the universe. So Hubble's law tells us that distant galaxies are receding from us, and the further they are, the faster they're moving away from us, which is just evidence for an expanding universe. So blue model. Space between galaxies expands, and obviously as a consequence, galaxies grow further apart. There's limitations to a blue model because obviously the galaxies are all on the surface of the balloon, which is not the case. There's obviously galaxies in the space in between the balloons. I've seen that on an exam question before. It asks for limitations of this model. Right, let's move on to age of the universe. So a very common exam style question. So Hubble's constant tells us that the speed of a galaxy increases by 65 kilometers per second for every megaparsec, or 3.26 million light years. So for a galaxy to be receding at the speed of light, its distance would be 300,000 kilometers per second. Obviously, it's got to be in kilometers per second, divided by Hubble's constant, which gives 4,615 megaparsecs. Times that by light years, and we'd have 15 billion light years. Galaxies can't travel that fast, therefore light cannot have been travelling for this length of time. So the universe must be less than 15 billion years old. Current greatest length of time is observed to be about 13.5 billion years. And what I'm going to show you next is how we can calculate that value. Right, so let's look at the age of the universe. So Hubble's law is V equals hd. And what we're going to use here is velocity is simply distance over time. I'm going to use capital T for the age of the universe. So we can make these equal to each other. So we end up with distance over time equals hd. So the distances cancel, and we're left with 1 over t equals h. So time is equal to 1 over the Hubble's constant, which might seem quite straightforward, which it is. The issue is dealing with the units of Hubble's constant. So let's have a look. So time is equal to, so we've got 1 divided by 65 kilometers per second per megaparsec. So that per megaparsec we can flip up to the top because it's a division under a fraction. So the age of the universe is going to be equal to a megaparsec divided by 65 kilometers per second. So what we want to do is to get that into seconds. So we need to know either how many kilometers are in a megaparsec or how many meters. So I'll do meters. So on the data sheet, you've got a parsec. So it tells you that 1 parsec is equal to 3.08 times 10 to the power 16 meters. So a megaparsec is 3.08 times 10 to the power 22 meters. So that's what we're going to use. So the age of the universe T is a megaparsec, 3.08 times 10 to the power 22 meters. And what we need to do is convert that kilometers at the bottom into meters as well. Meters per second. Meters cancel. 1 over 1 over s gives us the age of the universe in seconds. So that gives us 4.74 times 10 to the power 17 seconds. We can convert that to years. So what we need to do is the 4.74 times 10 to the power 17 divided by the amount of seconds in a year. So 365 days, you could use a quarter if you wish. Times seconds in a day, 60 times 60 times 24, which is 86,400. And that'll give you it in years, which is 1.5 times 10 to the power of 10. Or 1.5, sorry, 50, not 1.5, 15 billion years. All right, so make sure you know that. That comes up often. Right, let's try a practice question. Alright, so if you want to pause and try this one. Right, so in 2009, measurements from the Hubble Space Telescope yielded a Hubble constant of 74.2 plus or minus 3.6 kilometers per second per megaparsec. Calculate the maximum possible age of the universe. That's helpful, having that megaparsec there. Right, let's have a go. So first of all, we need to decide what value of Hubble's constant we're going to use. So we know that age of the universe is equal to 1 over h. For the maximum largest value of age, t, we need the smallest value of the Hubble constant. So we're going to do 74.2, subtract 3.6. So the Hubble constant we're going to use is 70.6 kilometers per second per megaparsec. Then we just need to do what we did last time. So t is 1 over h. So age is 1 divided by 70.6 kilometers per second per megaparsec. So we take the megaparsec up to the top and then put the numbers in. So we've got how many kilometers in a megaparsec, which is useful. So that's 3.1 times 10 to the power 19 divided by 70.6. That's in kilometers. That's kilometers per second. Kilometers cancel. So we're left with age. So according to that measurement, we get 4.39 times 10 to the power of 17 seconds. And then what we can do is divide by the amount of seconds in a year. So divide by 365 times 86,400 seconds in a day. And that gives us 1.4 times 10 to the power of 10 years. Or 14 billion years. Alright, hopefully you found that useful. And thanks for watching.